Welcome to The Explainer. Today, we're diving into thermodynamics. You know, the science of heat, work, and energy. It's basically the rulebook for, well, for everything.
So here's a question for you. What do a refrigerator, a car engine, and the entire universe have in common? Yeah, I know, it sounds like the setup to a pretty weird joke. But the answer is, they all play by the exact same set of unbreakable rules. And stick with me because by the end of this, you're going to know exactly what those rules are.
All right, here's the plan. We'll kick things off with the basic language, then jump into the first law. After that, we'll look at a couple of different functions, explore 4 ways things can change, compare them, and wrap it all up with a look at the engine of the universe. Sound good? Let's dive in. Okay, Section 1, the language of energy. First things first, we've got to learn to speak the language, right? I mean, pretty much everything in thermodynamics boils down to just 3 key ideas. 3 variables that tell us how energy moves and changes. So, first up we have heat, which we call Q. Now, the key thing to get about heat is that it's energy on the move. It's not something an object just has. It's the energy that flows from a hot thing to a cold thing. Simple as that.
All right, next up is internal energy, or U. Now, this is the energy a system actually has locked up inside it. If you think about a gas, it's basically all the energy from its little molecules just zipping around and bouncing off the walls like crazy. The faster they're all moving, the higher the internal energy is.
And that brings us to our third piece of the puzzle, work, or W. This is all about energy being transferred when something gets moved, a force causing a displacement. The classic picture here is a hot gas expanding inside a cylinder. As it pushes that piston up, that's literally the gas doing work.
Okay, but here's a super important point about work. It's all about perspective. The direction matters. So if a gas expands and pushes on the world around it, like our piston example, we say the work is positive. The system is doing the work. But if the surroundings push on the gas and squeeze it, well, that's work being done on the system. And we call that negative. It's just a sign convention, but man, it is absolutely crucial to get right.
All right, Section 2, the first law of everything. Now we get to see how our 3 new friends, Q, U, and W, all play together. This is where it gets really good, because they form one of the most fundamental rules in all of physics.
You can think of the first law of thermodynamics as a really strict energy budget. It's just asking a simple question. If you add some heat, Q, to a system, where does it go? I mean, it can't just vanish into thin air, right?
And boom, here's the answer. This simple little formula tells us everything. The heat you add, Q, can do one of 2 things. It can either increase the system's internal energy, that's the delta U part, delta just means the change in, U, or it can be used by the system to do some work, W. That's it. Energy in equals energy accounted for. Nothing's ever created or destroyed, it just gets moved around.
Okay, moving on to Section 3, a tale of 2 functions. Now, here's the twist. It turns out that not all of these energy variables are created equal. They don't behave the same way. And understanding this difference is, well, it's a total game changer for how you solve problems in this field.
So you've got 2 types, state functions and path functions. Let me give you an analogy. Imagine you're hiking a mountain. Your change in altitude only cares about 2 things, where you started and where you ended up. The trail you took doesn't matter. That's a state function. But the number of calories you burned? Oh, that absolutely depends on the path. Did you take the easy winding trail or the super steep direct route? That's a path function. It's the same here. Internal energy is like your altitude. It just cares about the start and end points. But heat and work, they're like the calories. They depend entirely on the journey you took to get there.
All right, Section 4, 4 ways to change. So if the path is so important for heat and work, you're probably wondering, what do these paths actually look like? Well, let's check out 4 of the most common ones.
First up is what we call an isochoric process. Fancy name, simple idea. The volume stays the same. Now think about it. If the volume is locked in place, the gas can't expand or get compressed, which means it can't do any work. So W is just 0. And our first law equation gets super simple. Q equals delta U. Every bit of heat you pump in goes straight into making those molecules move faster, raising the internal energy.
Okay, next path is isobaric. This time, the pressure is what stays constant. So what happens when you add heat? Well, the gas expands, which means it's doing work.
So that heat energy you added now has to split up and do two jobs at once. Part of it goes to increasing the internal energy, and the other part gets used to do that work of expansion.
So what if we could somehow keep the temperature perfectly constant? Well, that's called an isothermal process. And remember, internal energy is all about the temperature. So if the temperature doesn't change, the internal energy doesn't change either. Delta U is 0. And look what happens to the first law. Q equals W. This is amazing. It means every single joule of heat you add gets instantly turned into work done by the system, 1 for 1.
And for our last path, we have an adiabatic process. This is where you perfectly insulate the system. Think of it like a perfect thermos. No heat gets in, no heat gets out. Q is 0. So, if the gas still expands and does work, where on earth does that energy come from? It has to pay for it itself by using its own internal energy. And when internal energy goes down, the temperature drops. This isn't just theory, by the way. You felt this. Ever used a can of compressed air? The can gets freezing cold, right? That's adiabatic expansion in action.
Okay, Section 5, comparing the paths. We've just met 4 different ways a system can change. Let's line them all up and see how they stack up against each other.
This table is such a great way to see it all in one place. You can just look down the first column, isochoric, isobaric, and so on, and see exactly what's being held constant. And that one little constraint, that one rule for the path, completely changes how the first law works out and how work gets done. You see, isochoric, no work done, period. But for the other 3, the system is busy doing work because its volume is changing.
Now, if we were to plot these out on a graph of pressure versus volume, you'd see something really interesting. Both the isothermal and the adiabatic paths are curves that go down as the gas expands. But the adiabatic curve is always steeper. And why is that? Well, think back. In the adiabatic process, the system isn't just expanding, it's also getting colder. That extra cooling causes the pressure to drop off way faster.
And that brings us to our final section, the engine of the universe. So we've laid out the rules, right? The first law? But these rules lead to some really deep, really profound consequences for, well, everything. It's about more than just pistons and gases.
This quote right here, this is the heart of the second law of thermodynamics. And honestly, it's a bombshell. I love this analogy. If the first law is the universe's accountant, telling you that you can't create energy from nothing, you can't win, then the second law is the universe's tax man. It's even meaner. It says you can't even break even. In any real process, any real engine, you will always lose some energy as waste heat. You can never, ever be 100% efficient.
And that leaves us with this final, kind of mind-blowing question. If the first law says we can't create energy, and the second law says we're always losing some of what we have as waste, what's the endgame? What is the ultimate fate of all the useful energy in the universe? See, these rules, they're not just for engines. They point to a one-way street for the entire cosmos, an arrow of time. Every single thing that happens pushes the universe toward a state of greater and greater disorder. So the big takeaway here? Energy doesn't just have rules. It has a destiny.